I'll start this video by asking the question, why do we need mathematical models? We know that the design of a physical control system requires a comprehensive understanding of the dynamics of the system. Such an understanding can be captured by a mathematical model, and that is the reason why we need to have a mathematical model for the system under investigation. The mathematical model we come up with is usually in the form of a set of mathematical equations. A mathematical model is powerful because in some hypothetical situations, we can simulate the system using the model that we build. Also, sometimes we may have different design options for the system being investigated. In this case, when we have a good mathematical model, it serves as a foundation for us to compare different design options. And this will allow us to choose the best possible option for the system that is being investigated. We have come across some mathematical models already. The first type of mathematical model that we have already encountered in our prior study is a differential equation model or a difference equation model. This type of mathematical model is also known as the input-output model because it does show us the input and output relationship of the system that we are interested in understanding. Another type of mathematical model is called the state space model, and this model is what we are going to focus in the near future of this subject. The state space model is also called a state variable model. Sometimes you may hear me mention it as a state space representation. So all these terms, they mean the same thing. And this model uses a vector matrix representation. And that's why I mentioned earlier in the subject that we need to have a good foundation in matrix operations. Just as control system design itself, building a mathematical model of the system we investigate is also an art and a science. It is a non-trivial job and it requires a lot of skill. Fortunately, feedback is forgiving. So sometimes we can get away with simple models, and this model can also be quite crude, as long as the model captures the essential features of the problem we study. That is why in this subject, the mechanism of feedback plays such an important role. On this slide, you will see a step-by-step approach to dynamic system modeling. The first step is to define the system under investigation and define the components associated with the system that we study. Then we need to formulate the mathematical model and list necessary assumptions. The third step is to write out the mathematical equations describing the model that we come up with in the second step. Then we need to solve the equations for the system output. Once we solve the equations, we need to examine the solutions, and we also need to examine the assumptions because we may need to modify the assumptions. Very often, this modeling process is an iterative process. As I mentioned in the past, for engineering design, it is rarely a one-go activity. We may have to modify our assumption. We may have to go over the design a few times until we reach a satisfactory solution. On this slide, you will see a general differential equation for a linear continuous time system model. How do we solve this differential equation model? A general rule is that for mechanical systems, we can use Newton's law. And for electrical systems, which might be more familiar to us as electronic engineers, Kirchhoff's voltage and current laws serve a good purpose here. To save lecture time, we will do some modeling practice in the tutorial. Now let me move on to the analogous systems. Before I give the definition of analogous systems, I would like to give you two examples here. Let us consider a spring mass damper system and an RLC circuit. And I will show you two graphs. The top graph is a spring mass damper system, and the bottom graph is an RLC circuit. So how do we mathematically model these two systems, which seemingly look very different? For the spring mass damper system, we can write out the differential equation model for this system using Newton's second law of motion. And the equation is presented on the slide. For the RLC circuit, which is possibly more familiar to us, we use KCL to write out the equation. That is, the current flowing into the node should be equal to the current flowing out of the node. And the equation is also shown on the slide. By the look of the two equations on the slide, you may say, I don't think there's any similarity between them. But wait a second. If I do this, I let Vt, which is the velocity of the mass, be equal to the first order derivative of yt with respect to t, and yt here is obviously the displacement of the mass. Then I can rewrite the top equation as this. Now if you compare the new equation with the KCL equation you derived earlier, you can say that they do look very similar. And this shows us what analogous systems are about. Analogous systems exist for a variety of systems. They may be electrical systems, there may be mechanical systems, there may be thermal systems and fluid systems. As the two examples I gave you in the previous slide, you can see that the first system is a mechanical system and the second system is an RLC circuit. On the surface, they don't share any commonality, but they actually arrive at the same describing equations. And these two systems are analogous systems because they have the same mathematical equations to describe them. The existence of analogous systems allows us to extend the solution of one system to all of the analogous systems with the same describing equations. Now let me explain what linear approximation is. We know that a majority of physical systems we encounter are linear only within certain operating ranges. Generally speaking, all of the systems become nonlinear when the variables are increased beyond limit. And the reason we want to approximate a nonlinear system with a linear model is because we can use the nice properties of linear systems to study the model. And what are the nice properties of a linear system? There are two very nice properties. They are the superposition law and the homogeneity law. Now let me further explain what they are. So these two properties belong to linear systems only. They are very powerful. Now first look at the superposition law. Let's say if the system input is ET and the output of the system subject to the input ET is VT, and the relationship between ET and VT is given by this linear function L. So what is the superposition law? When we have the input E1, it produces the output V1. When we have the input E2, it produces the output V2. I have omitted T for simplicity. We know that all of the input and output variables I just mentioned, they are functions of time t. Now the question is, if the system is subject to both the input E1t and the input E2t, what will the output be? And under the superposition law, the output would be a summation of the individual outputs generated by the corresponding inputs. There is a practical use of the superposition law. Let's say if a system has two inputs, one input is called a reference input, and I'll write it as RT. And the system also suffers a disturbance signal, and that disturbance input is called DT. My question is, what if the system has both inputs, RT and DT, acting on it? What the output should be? To solve this problem, we can use the superposition law. How do we do it? Under the superposition law, we can treat these two inputs separately as if they are totally independent. In other words, we know that RT produces the output YRT, and we know the disturbance signal produces the output YDT. And when the system is subject to both RT and DT, the output of the system should be, under the superposition law, equal to YRT plus YDT. It is as simple as that. And when you are seeking YRT, you don't have to worry about the existence of DT. You only need to treat YRT, which is produced by RT, by ignoring the existence of DT. And the same thing applies to YDT. So you treat the two input signals completely independently, as if the other one did not exist. You find the individual output generated by the corresponding input, and then the output of the system is simply a summation of the two outputs. The second nice property of a linear system is homogeneity. And this property basically says the scaling factor that is applied to the input is preserved by the linear system. So we know that with these nice properties of a linear system, we can study the system in a much better way. So now the question is, how can we build a linear model, or how can we perform linear approximation to obtain a linear model of a nonlinear system? There is a condition attached here. And the condition is we can only build a linear model of a nonlinear system by way of linear approximation in the neighborhood of a chosen operating point and assuming a small signal condition. So I'll give an example of linear approximation. So I just mentioned to do linear approximation, first we need to choose an operating point, and then we can only build a linear model around the operating point, assuming a small signal. Now, let's say the input of the system is xt, which is the excitation signal, and the response, which is the output, is yt. And the relationship between xt and yt is given by the function g. We choose an operating point, and usually the operating point is the equilibrium point of the system. Let's say for this system, the operating point is x0. We can use Taylor series expansion to find yt. So y is equal to g of x, and the equation on the right-hand side of the equal sign is Taylor series expansion. To do linear approximation, we only keep the first order term of the Taylor series expansion by removing all of the higher order terms. Therefore, we only keep the constant term g of x0 and the first order derivative of g with respect to x evaluated at the operating point, and all of the higher order terms you can say are removed from the approximation. And this guarantees that we satisfy the small signal assumption. By deleting all the higher order terms, the approximation becomes a linear model. And at the end of the slide, you can see the linear equation that is associated with this approximation process. The two things that you need to remember are you need to choose an operating point and you need to assume a small signal condition. Let me give a practical example of the linear approximation process. Let us consider the pendulum oscillator. We want to model the swing action of the pendulum. First, we need to choose an operating point. And the operating point for this example is obviously the equilibrium point, which is when the pendulum stays stationary. That is, the swing angle theta is 0 degree. Next, we need to assume a small signal condition. That is, we need to assume that the pendulum swings in a small range. Based on the knowledge of the pendulum, we can easily write out the equation describing the movement of the pendulum. And that equation is the torque equation, T here, capital T. To find the linear approximation of the equation described by t equals mgl sine theta, we need to use Taylor series expansion. And when we use the Taylor series expansion, we only keep the constant term and the first order derivative term. In other words, we delete all the higher order terms, and that is shown by this equation. And the small range assumption for the pendulum example is approximately minus 45 degrees to 45 degrees. And when we say that in this range, the approximation is reasonably accurate. As a matter of fact, when the pendulum swings between plus minus 30 degrees, the error of this model compared to the actual nonlinear pendulum response is only 5%.